let's say 100 years ago from today, and someone tells you that there would be a time in future when cars will drive by themselves without any interaction with human drivers. I would have definitely laughed over this and thought of it as a joke which can never be achieved. But when we talk about it today and even look around us, we can see that how close we are to bringing this dream into a reality. We are only I repeat, very few years away from the time when we'll be riding in driverless cars in our daily lives. So, if I vaguely define self driving cars, then they are vehicles that are capable of sensing their environment and moving safely with almost no human input at all. All the leading companies and researchers are in a race to reach that benchmark and are working very tirelessly to achieve that. And hence, we are also presenting our small but effectful contribution to that research, teaching cars to see a future of self driving cars, lane detection system using road lane edges. But before going into the details of the project, I'd like to introduce my team. So this is our team who have worked on this project, and also our supervisor who has been very cooperative throughout. So when I talk about driving and all the tasks related to it, they are very easy to perform for any human driver, but at the same time very difficult for a machine. And hence, self-driving car should be created with very high accuracy. The Uber self-driving car crash from March 2018 that took place in Arizona is a very tragic example of how human lives can be at so much risk just because of some less efficient detecting algorithms in the vehicles. So it is very important to design these algorithms with utmost precision. Now that it is a well-known fact that what self-driving cars are, let's dig a bit into their working. So a fully functional self-driving car comprises of a lot of subsystems, as shown in the flowchart over the screen. It contains several sensors such as lidars, radars, GPS systems, and cameras, only to name a few, which provide data to the self-driving cars. All these sensors capture different kind of data that help for the further modules to work upon them. That data is used to perceive and map the environment. Environment perception is the module which detects all the dynamic and static objects around the car in its environment that are expected to affect its motion. And then the motion planning module plans the motion of the object from one point to another point, which is basically the source and destination for the self-driving cars, based on the localization map that were generated in the environment mapping module. Then the controller module controls the longitudinal and lateral control of the vehicle based upon the data provided by the previous modules. And finally, actuation is the process of converting this controller data into actions, and that's how the car runs and controls its steering angles, velocity, acceleration, brakes, etc. So our project focuses on the environment perception module of a self-driving car, or more specifically on visual perception of the vehicle. Visual perception is providing eyes to the system. And to do that, we only use one sensor, which is a front mounted camera, because only a camera can work as eyes, which will work as the eyes of the system. Now, let's talk about the aims and objectives of our project. So, we have to set up a simulated environment for a self-driving car, which will be used to test our algorithm and which will be used to run our system. And we also have to create an algorithm that should detect road lane lines. The system should be able to take dynamic data. So our whole system is based upon taking dynamic data, and we will not use any predefined pictures or database of videos to detect lines, but we'll use dynamic data, images and frames from the road, and that will be used to detect lane lines. And then the system should be robust enough to detect lines under all kind of weathers. So the system should be able to detect lines even when the lines are not visible enough due to maybe low lighting or raining, and we have tested our algorithm in all these conditions. So now, to achieve all these objectives, We set up an environment in the Carla simulator and we use a vehicle as an actor, which we can use to test our algorithm. We place a camera on the front of the car, which will be our main sensor, and we'll use it to capture dynamic images of the road, and then implement our algorithm on those images and also dynamically show the results. We have used Huff transformation technique to detect lane lines. Huff transformation is a very famous feature extraction technique in computer vision, but we cannot directly apply this technique and we have to fine tune the frames a bit, and that process can be seen through the algorithm in the flowchart over the screen. So at first we capture the frame through the camera that we have placed over the top of our vehicle and convert that frame from RGB color model to a grayscale image. Then we perform a Gaussian blur on the image. Gaussian blur decreases the noise of the image and provides us with a much refined image. Then we use Kenny edge detection, which is again an edge detection algorithm to detect edges of our image. And then we draw a trapezoid on our image to find the region of our interest. And finally, we perform Huff transformation technique to detect lines. We then filter out these lines in the last two steps to get better results. Now let's look at the final results. We have tested our algorithm in 6 different weather conditions to check the robustness and accuracy of our algorithm, and our algorithm almost performed very well in all those 6 weathers. This is the first weather, which is clear noon, and the lane lines are very much prominent due to good daylighting. We drive the car along different lanes to see how the algorithm works with lane changes. On the right side of the screen is the simulator environment where we are driving our vehicle. And this is the screen that the camera is capturing. We have placed a front mounted camera over the vehicle, and this is the screen that is captured by the camera. And on the left side is a black and white visual of the same screen where you can see the exact detected lane lines of the road. The second weather is a clear sunset. The output shows a trapezoid in front of the car, which is approximately equal to the size of the vehicle, and the trapezoid is the region of interest that we had detected in the algorithm. The output also shows two lines, red and green, so the red lines are a fairly rough output, while the green lines are the more refined ones, which we filter out through slope value. Green lines are the perfect depiction of the lane lines that are present on the road. The third weather is now of cloudy noon, where the lines are slightly less visible due to the clouds and shortage of daylight compared to the previous two weathers. But our algorithm still detects nearly perfect lane markings even in lesser light. The fourth weather is that of cloudy sunset, and again the lines are less visible because of the clouds. Now we have provided rain in the simulator. The fifth weather is of hard rain noon, and due to the rain, the road has a shiny surface over it. And it is even difficult for a human driver to see the correct lane lines when it is raining. The sixth weather is hard rain sunset. And again, the surface is very shiny and the lines are very much less visible. And our algorithm also gives a slightly less accuracy in these two rainy weathers, but it is still able to detect lane lines and does not fail completely in these two situations as well, even when the lanes are not very much prominent. This was all about our results, and as you can see that our algorithm and our system has performed very well during all the testing phases. So let's move on to the technologies that we have used in our project. At first, we have used Scala Simulator for simulating a self-driving car environment, and all the things that you saw, how we provided a vehicle, how we were driving that vehicle, how we were accessing a camera sensor, and how we were changing weather. This all was done in a simulated environment, just like the real world. Carla is basically an open source simulator for autonomous driving research. We can create our own environment by using different vehicles and pedestrians and sensors to test our self-driving car algorithms, as we have done for our project. The programming language that we have used is Python. All the algorithms are implemented in pure Python language. The third thing that we have used is a Pygame. Pygame is basically a cross-platform set of Python modules designed for writing video games. And we have used Pygame in our project to control the vehicle and its actions. Fourthly, we have used OpenCV to implement our main lane detection algorithm. OpenCV is a computer vision library that we can use in languages like Python and Java to work on images. Fifth, NumPy is a library for the Python programming language, adding support for large multidimensional arrays and matrices. And we have used it to convert our image frames into arrays of pixels to perform feature extraction over them. Our data was consisting of images that the camera was capturing for us, but to perform feature extraction techniques and have transformation on those images, we had to convert them into a set of pixels, into arrays of pixels. So we have used NumPy to do that. So this was all about our project, and as we say that nothing in this world can be perfect, so isn't our project. The project still has a lot of scope for future works, as the algorithms and the systems can be improved to perform even better in so many more situations. But for now, that is all for our project. Thank you so much for listening, and thank you so much for your time.